we have briefly reviewed them last time. And also we have briefly reviewed the functional groups concept and what kinds of intermolecular forces and their effects on chemical properties. And also for something new, we have learned different notations to represent molecules. Especially, I asked you to learn to draw how to draw skeletal structures, and also Newman projection is something new, and we will continue to learn this time. So before we start, I'd like to ask you to keep in mind some of these things, and really try to all go to watch the 7 short videos by Professor Chu on the nomenclature. And the link is, if you open Moodle, the link is on the left column. And under the section of the additional resources, you can see 7 videos here, okay? And also next Tuesday, so before the class begins, so it's 9 a.m., the nomenclature drill will be open, so you can go there. It's not for credit, but it has 10 problems in it you can try to solve. And also, I noticed that around 20 of you haven't signed up for the tutorial group. So although the majority of you guys have already signed up, so just remember to sign up for the tutorial group. And if you have any clash of time, or you have some problems, you can ask the tutor about it, okay? And so at the end of the last class, I show you how to draw the Newman projections, and the rule is pretty simple. So I'm going to go through it very quickly. So the front carbon is a dot, and the circle is back carbon, and you have the front hydrogen, and you have the back hydrogen, okay? And you have 2 extreme conformation. One is the staggered, which these substituents are equidistant to each other. And another extreme conformation is this, what we call the eclipse. So all the hydrogens are paired up. And if you look at these directions, you will see the red hydrogen will cover the blue hydrogen, okay, which one of the extreme conformation. And the SN also have a lot of conformations between these two, which you can present like this. And we also learned how to quantify these kind of conformation, which is the concept of a dihedral angle. And to sum it briefly, it's just to the angle you need to turn about the CC bond. So these 2 hydrogens can be eclipsed with each other. And for those 2 extreme conformers, we have also show you that the dihedral angle, for example, this one is 60 degrees, and these blue one and the red ones are 180 degrees apart. But for the eclipse, you can see that they do not have any dihedral angle, so the dihedral angle is 0 degree. So you don't need to turn any sigma bonds to make these eclipse, because they are already eclipsed. And so at the end of last class, I show you that those kind of conformations have energy consequence. So what do I mean? So actually, if you start from this kind of eclipsed conformation, you have the red hydrogens, and here is a green one, eclipsed. You can see their energy level is pretty high, right? And then if you turn the red hydrogen 60 degrees clockwise to here, which now you become another extreme conformation, the staggered, then you can see the energy level is pretty low. And then you turn 60 degrees again, the energy level arises, okay? So what we call here is that these very high energy level is relatively strained. So because there are internal energies within this molecule. And if you have these kind of staggered conformation, the energy is very low, okay? That's what we call a relatively relaxed, because the energy is all gone. Every hydrogen is very comfortable with its positions. So you can see with the highest energy is 12 kilojoule per mole higher than the low energy, right? And the high energy, what we call why this energy would exist, is because there is a torsional strain. And the definition of torsional strain is that the strain due to the groups brought together. So which means that the strain results from the eclipsing of bonds. So it's not because the hydrogen and the hydrogen themselves have some clash with each other. It's because this bond and this bond are eclipsing. So because of the eclipsing of these bonds, there is energy, and this kind of energy is string is called a torsional string. Okay. So if you do a simple calculation, you see the highest energy level has 3 pairs of hydrogens eclipsing to each other. So you can see we write here 3 pairs of hydrogen eclipsing interaction. So which results in a 12 kilojoule per mole higher energy than the relaxed one, where we set it as 0. So that means each pair of the hydrogen-hydrogen eclipsing interaction, or the torsional string, is 12 divided by 3 is 4 kilojoule per mole. Okay, very simple calculation. But 12 kilojoule per mole is actually a relatively low energy barrier. So under room temperature or some relatively normal temperatures, so these conformers, because they can overcome the 12 kilojoule per mole energy barrier, so the ethene, the sigma bond between the two carbons is actually rotating like here rapidly. So in this case, what you observe is an average of the properties between all these numerous numbers of conformations. And if you recall that usually conformers cannot be separated because usually the conformer's energy barrier is very low. So you cannot say because there is energy levels, I can isolate the lower one because it's more stable. No, because under room temperature or normal conditions, these bonds are rapidly rotating. So you cannot isolate a single one of them. Okay. So if we move from ethane to butane, now butane has 4 carbons. It's a more complicated system. So now you have 2 types of CC bond. One is C1, C2 here, and the other is C2, C3 here. And this one is similar, it's the same as the C1, C2 because it's symmetry, right? So if, we can start with the simple one. So the C1, C2. Again, I asked you to look through this direction. So you put the C1 closer to you and the C2 in the back. I will show you what's the real model looks like. So this is butane, right? This is C1 and this is C2. If you look at this directions, you can see this carbon is closer to you with 3 red hydrogens, and the back carbon, or the substitution is reviewed here. So this is the hydrogen, this is the hydrogen, and this is not a methyl. This is actually an acyl group. Okay, so we can be clear about this structure. The carbon close to you, 3 hydrogens. The carbon away from you has 2 hydrogens and 1 acyl group. So with that, so we can start to draw the Newman projection of this. So there are 2 extreme ones, like ethane. So this one is staggered. So the front carbon, 3 hydrogens, the red ones. And in the back, there are 2 hydrogens and 1 acyl group. And so the dihedral group of the staggered, if you remember, it's 60 degrees, 60 degrees, 60 degrees. Okay. And for the eclipse conformation now, so you have to put the acyl group like eclipsed with the hydrogen here, right? So dihedral angle, there is no dihedral angle because they are eclipsed already, and the 2 hydrogens eclipsed, 2 hydrogen eclipsed. So the same thing is that between these 2 extreme conformers, there are numerous conformers between them, like these. You can quantify this angle. It's within 60 degrees and 0 degrees. Okay. So so in this butane molecule, if you look at the C1, C2 bond, the torsional string of these kind of this eclipsed conformation is actually 6.5 kilojoule per mole. So the ethane has the 12 kilojoule per mole. So the butane C1, C2 bond is even lower, only 6.5. So it's rapidly rotating. So if you look at through the C2, C3 bond, so it's a bit more complicated. So let me show you here. So if you look through this CC bond, okay, this is C2. So the C2 has 2 hydrogens and 1 methyl. And in the back, the C3 also has 2 hydrogens and 1 methyl, okay? now the Newman projection will seem differently than the C1, C2 bond. So the staggered is that now we have a front carbon with a methyl group, the back carbon with also with a methyl group. So the staggered has the CH3 and the CH3 opposite to each other. And so this particular staggered conformation is called anti. So the anti is defined by that the big substitution of the front carbon and the big substitution of the back carbon, the dihedral angle between them is 180 degrees. Okay, and another staggered conformation. So you can rotate the back CH3 into 60 degrees dihedral angle with the red CH3 in the front carbon. So now the dihedral angle is 60 degrees, right? So the 2CH3 is closer compared with the staggered conformation, which we called anti. So this kind of staggered conformation with CH3 60 degrees apart is called gauche. Okay, and so they have special names for the staggered conformation with these built-in structures, and also all the other structures with two big substituents on the front and on the back separately. So it's very easy to realize that the gauche is actually less stable than anti, right? Because the two big substitution is now closer, so they repel each other. So so besides the two staggered conformation, we also have two eclipsed conformations. So, but we don't have special names for them. Okay, they don't have names, but they are just eclipsed. So one eclipse is that the two big methyl group is eclipsing. So the dihedral angle between the two methyl group is 0 degree. So another eclipse conformation is that the CH3 on the back is eclipsing with one hydrogen, not methyl, hydrogens in the front, so 0 degrees. And another pair of, the methyl on the front is eclipsing with one hydrogens on the back. So these are the two eclipsed conformations. So that the difference is that this one is methyl-methyl eclipsing, and this two is methyl-H eclipsing. So if you have, again, those kind of rotation has consequences in energy. Okay, so we have some data listed here. So this one we already learned. Hydrogen eclipsing has 4.0 kilojoule per mole energy cost, and hydrogen methyl higher because methyl is bigger. It has 6.0. Methyl is even higher. It has 11 kilojoule per mole because they are bigger. And the methyl gauche, like 60 degree apart, it's a 3.8. But you need to notice that hydrogen, if it is gauche, it's like 60 degrees with any other substitutions, we assume that the energy cost is 0. So when you do the calculation, you don't need to consider the gauche interaction between any hydrogens and substitutions. So with these data, we now can calculate the torsional strain of different kind of conformations of a butane C2C3 bond. So let's go one by one. So the first one, the staggered, oh, sorry, it's a typo. Okay, so the anti has 0 kilojoule per mole. Why? Because all the Gaussian interactions, the 60 degree apart interactions has hydrogen in it. So hydrogen, methyl, hydrogen, methyl, hydrogen, methyl, hydrogen, hydrogen. So no energy cost whatsoever. So another staggered conformation, gauche, we learned that it's less stable. Okay, it's because the methyl-methyl interaction. So you see the methyl-methyl gauche is 3.8. Now we have 3.8 of this. But all the other gauche interaction containing hydrogen, so there is no energy cost in the rest of the molecule. So the total energy would be 3.8. So eclipsed, more unstable. So you can see we have 3 pairs of eclipsed interaction. So hydrogen methyl 6.0, hydrogen hydrogen 4.0, and hydrogen methyl 6.0. So the total energy is 16. So much higher than any of the staggered conformation. So how about another eclipsed conformation? So we have a methyl-methyl, again, 11. We have hydrogen-hydrogen, 4. And the hydrogen-hydrogen, 4. So 19, even higher. It is because this methyl-methyl eclipsed interaction is really big in energy cost. Okay. So, and you can also draw a graph of a plot of the dihedral angle and the energy relationship. Okay, so different from the SN, which is very symmetry. And this is also symmetry, but on this part it's not. So you can see, based on the calculation, there is an energy gap 3.8, 16, and the 19 is the highest energy cost because of the meso is cost almost 11 kilojoule per mole. Okay, but again, even 19 kilojoule per mole energy cost is actually very small. So just like SN, what you observe, the built-in you observe is an average of the properties of all these individual conformers, these extremes, and all the conformers between them. So you cannot say that you can isolate a built-in conformer with like Gauss, anti, or eclipse conformation. That's not possible. So okay, so I already showed you how to calculate the energy level with the built-in system. So now we can have some practice about more complex, like the two-meso built-in system. So this time I will show you how to do that, but you need to practice after the class, and there are some. Okay, let me show you. Okay, so let me put it on the screen. So whenever if you encounter this kind of questions in the exam, so if I ask you to draw the conformations, staggered and eclipse of C2, C3 bond of a molecule, okay, what you first do is that you need to figure out what's the molecule, right? So 2-methylbutane looks like this, all right, and the C2, C3. So this we can assign C2, and this is C3. So first, you need to figure out what kind of substitutions are there on each carbon. All right. So on the C2 carbon, you can see we have a methyl group, and this one we just have 2 hydrogens, right? So you write it down. You have one methyl group, 2 hydrogens. All right. And for the C3, it's different. It has 2 methyl groups and 1 hydrogens. All right, you have C3, hydrogens times 2, and oh no, hydrogen times 1. But methyl, we have 2. All right, so now we can start to draw the staggered conformation first. Okay, so if you look at this molecule through this direction, put the C2 in the front. Okay, I will draw here. So front carbon, back carbon. C2, we have a methyl group, and the rest are the hydrogens, okay? And how we draw this conformation is that we keep the front carbon not moving, but just rotate the back carbon. So what we can do is we can copy it, but you can't on the exam, okay? And okay, now let's do the C3 here. So on the C3, we have 1 hydrogens, and because we draw the staggered conformation first, so it's 60 degrees apart, right? So so we have 1 hydrogens here. The rest are 2 methyl. All right, then we rotate this hydrogen to here. So we have another staggered conformation, right? We have hydrogens here, and methyl here, and methyl here. Okay, then another 60 degrees. Now the hydrogen is here, and the 2 methyl groups are here. All right, so that's all the staggered conformation we have drawn, and we will look at the energy cost later. But now let's draw the eclipse conformation. So again, you draw a circle. That's the back carbon. So I'm drawing that ugly because the iPad Apple Pencil is really hard to use. So my actual drawing is actually much better. Okay, just for your information. So again, the front carbon has 1 methyl, 2 hydrogens. Okay, and now we have eclipsed. So we can put the hydrogen eclipsed with the methyl first. All right. eclipsed. Okay, then 2 methyl here, methyl. Oh, I forgot to copy that. So another one, methyl, hydrogen. So now we put it, let's copy it first. So we can rotate the hydrogens to here. Now the hydrogen is eclipsing with this hydrogen and methyl here, and then the same, another 120 degrees, I think, and then this hydrogen and this methyl. Okay, now we have all 6 staggered and eclipsed conformations drawn on this whiteboard. Okay, and it's time to calculate the energy difference. Okay, so the first one, so they are all gauche to each other, right? But all the gauche with hydrogen, they don't have energy cost. No energy cost. The only energy cost is between methyl and methyl. All right, which is methyl gauche 3.8. All right, so it has 3.8. So the total is 3.8 kilojoule per mole. How? Okay, let's see the second one. Now the hydrogen doesn't have energy cost, not here, But now we have 2 pairs of methyl gauche, right? This is 3.8. This is 3.8. Now we have 7.6 kilojoule per mole. For the third one, so no energy. Okay, only one pair. So which is 3.8. So the total is 3.8 kilojoule per mole. So let's move on to the eclipsing. Okay, the eclipsing must have some higher energy, right? So we have methyl hydrogen, and the methyl hydrogen. Okay, so 3 pairs of methyl hydrogen interactions, which is eclipsing. The hydrogen methyl is 6.0. So we have 6, 6, 6. So the total is 18 kilojoule per mole. Okay, the second one. The second one has methyl and hydrogen methyl. So we just need to find out in this chart. So methyl is 11. So hydrogen is 4.0. And methyl hydrogen is 6.0. Okay, 11 plus 10, which is 21 kilojoule per mole. And the last one, okay, we have methyl hydrogen, exactly the same. So 11, 4, 6, 21 kilojoule per mole. Okay, so if I put this kind of problems on the midterm 1, so this kind of presentation completes your answer, and you will get everything you want. Okay, so full marks. All right. And so let's go back. So for the questions, you said should the substitute method on the C2 due to the C? Oh yes. But if you draw the other way, it's the same. But if you let's say yeah, I made a mistake here. But so if you actually so this one is actually C2. Yeah, C3. All right. So if you look through these directions, you can draw a different 6 of different staggered and eclipsed conformations, right? Because now the 2 methyl is on the front, but the energy difference won't change. So on the exam or on the midterm, I will draw clearly about which direction you should look through to draw the all these Newman projections. So I will give you the arrow here, like this or this. So you don't need to worry about, oh, should I look through this bound here or there? Okay, so that should make it clear for you. And yeah, hopefully that answers your questions. Yes. So if I asked you to draw all the, yeah. So this question is vague because I asked you to draw the most strength, right? So if on the exam you draw the most strength, it's fine. Okay. But if I will I will be very clear on what you should. So I probably will say, oh, draw all the conformers, but point out the most strength one. Okay. So then you need to draw all of them. But if I say you just need to draw the most stringed, staggered, and eclipse, you just need to give me two. One of them is the most stringed staggered conformation. The other is the most stringed eclipse conformations. Okay. Here I just want to show you how I work this problem out. Okay. So in the exam, I will be very clear about what you should do and what you need to present to get all these information. Yes. Okay, so let me get back to the. So before, as I pointed out in the roadmap of study, eventually we will go to the cyclohexene conformation, right? And so before we go to cyclohexene, I will give you some like brief introductions of smaller rings, like those conformations with smaller rings. All right. So now what you see is the 3-member ring, 4-member ring, 5-member ring, and the 6-member ring. Okay. The 3-member ring is like a triangle, right? And so if you recall that in an acyclic system, that's what we call a linear system. So the sigma bond can rotate, right? But and because of the faster rotation, so ethane and butane interconverts very rapidly. And the actual properties we observe for these linear molecule is an average of the properties of all their conformers, right? But in the ring system, it's quite different. So the rotation in the ring system is actually restricted by the ring structure, because if you have a triangle, right, you can, for example, you have this 6-member ring here. So if you just want to rotate one single CC bond, it's not possible, right? Because it's a ring, and because of the ring string or the ring structure and the restricted bond rotation. So the result of this is that now the ring has 2 faces. So, and because of 2 faces cannot interchange with each other, we have a name for that. So the cis is what we call for the face for the conformers, for the stereoisomers that have the substitution on the same face, and the trans is on the opposite face. So what do I mean? So for example, this cis 1,2-dimethyl cyclopropane. Cis 1,2-dimethyl cyclopropane. So these 2 substituents is on the same face, the upper face, the top face of these ring plane, right? So now we call it cis. And for the trans isomer, which this methyl and this methyl is on the bottom, this methyl is on the top face. So, and these 2 cannot interchange, and this one we call the trans. And for the 4-member ring, it's the same. If I have 1,3-dimethyl substituents, so it's on the same face, then it's called cis. And for example, this bromide and this acyl group on the opposite face, we call it trans. But this is actually a pretty good exercise to name the compounds, because it has a cyclic structure in it, and it has hydro atoms. So practice on your own, okay? And as I said, they cannot interconvert to each other, and they are not conformers, because as I said, conformers can interchange with each other and cannot be isolated as a single conformer, but these can, okay? So cis and trans, they are 2 compounds and can be isolated on their own. So actually, you may be able to buy this pure form of the cis and the pure form of the trans separately. Okay, there are several types of strings in cycloalkanes. So torsional string, we already talked about it. It's because of the eclipsing of bonds on the neighboring atom. So if the 2 bonds are eclipsing each other, that means that they have a torsional string. Okay, and the second one is angle string. So angle strength is defined by the expansion or compression of bond angles away from the optimized bond angles. So you all know that sp3 hybridization has a 109.5 degrees bond angles, right? So if in your structures, your bond angle is deviated from this normal angle, we say that it has an angle strength because the angle is different. So for example, the cyclopropane is the plane structure, right? A planar structure, it has 60 degrees bond angle between this CC bond and this CC bond. But the optimal sp3 hybridization has 109. So this has very large angle strength, okay? So it's cyclobutane if it's a planar structure, but in reality it's not. We'll learn it later. And so the 5-membrane, if it's a planar structure, it has 108 degrees, so only 1 degree. So we say cyclopentane really, if it's a planar structure, it doesn't have angle strength because it's very close to the optimal sp3 angle, which is 109.5. And cyclohexane, it's if it's a planar structure, it's 120 degrees, has angle strength, but in reality, it's not a plane structure. Okay. So the last one, someone asked me that what is a steric string? So steric strings is actually a repulsive interaction between non-bonded atoms. So they cannot. So you cannot say. So if a carbon is linked to another carbon, you cannot say they have a steric string because they are bonded. So we are only looking for non-bonded atoms to have steric strings. All right, and we will talk about examples of these. So. Actually, the string energies of those cycloalkanes, it's combined strings of torsional, angle, and sterics. So you can see 6th membrane doesn't have any string energies, and which is really a special case. We will pay a lot of attention to it, and 3-membrane and 4-membrane are very high in energy. 5 is lower, and you don't need to worry about the large ring from 7 to 14 members ring, and these will not be covered or required for this class. So let's go there one by one. So 3-membrane has a very high string energies. So what kind of strings are there? So because 3-membrane, if you put 3 atoms linked to each other together, so you only can have a planar structures, right? And so because of the planar structure, all CH bonds are eclipsed to each other, and with a carbon-carbon-carbon bond angle of 60 degrees. So let's make it clear to see the structure in a 3D mode. So you can see these 3 carbons are linked together in a planar structures. And if you look at this CC bond, see, they are eclipsing with each other, all of them. If you look at this bond, 2 pairs. If you look at this bond, 2 pairs, right? And because of all these factors, if we consider together, so it has angle strain because its angle is 60 degrees, right? Away from 109, and because of the eclipsing, which is torsional strain because the eclipsing of bonds of this CH bond and this CH bond. So all those strings combined makes the cyclopropane a very strained molecule indeed. Okay, if you draw the Newman projections based on 1 CC bond, although this is not required because it's a cyclic system, only a linear system is required for you to draw Newman projection. But I'm going to just show you here as an eclipsed pair of hydrogens and another eclipsed pair of hydrogens here. Okay, cyclobutane. So planar cyclobutane, okay, like the planar cyclopropane, it has all CH bond eclipsed together. All right, let's see here. Again, all CH bond eclipsed together, right? Okay, and but if the if this is the Newman projection, all pairs of hydrogen eclipsed, so that means it's very high in energy. Okay, but if you bend this these bonds, so now you make it a bent structure of cyclobutane. Now it's kind of favored. So because why? There are 2 factors in here. So bent cyclobutane actually increase the bond, increase angle strain because in the planar, it has 90 degrees. It has 90 degrees bond angle. And if you bend it, now the degree is actually lower than 90 degrees because you bend the CC bond. It's more like not in a plane. The angle becomes sharper, right? So the angle strength does increase. But the good thing is that because it's bent structures, now the CC bond is not quite eclipsed with each other, okay? So the torsional strain decreased. And the overall effects is that this bent structure is actually more favored than those planar structures. Keep that in mind. So to find membrane is quite interesting. So if you heard me that the bond angle, if the cyclopentane is planar structure, is 108, very, very close to the sp3 optimal hybridization, which is 109, right? But the bad thing is that if you put all these carbons on a plane, all these hydrogens, again, are eclipsing with each other, okay? So it doesn't, if it's a planar structure, it doesn't have angle strain, but it has a lot of torsional strain, okay? So what cyclopentane decides is that it will adopt what we call an envelope shape. So what does it mean? What does it mean? So 4 carbons of the cyclopentane decides that, oh, we are pretty comfortable. So they said to the rest of the carbon that you just get out. Okay, we don't want to. 4 of us on a plane is quite comfortable now. We don't want another one. So if you look at these cyclopentane structures, all right. So this carbon 5, carbon 4, carbon 3, carbon 2. Okay, they are on a plane, right? And they kick this carbon 1 out of this plane. So you can see plane out of plane. Okay, clearly, right? So why does it call the envelope? It's because the 4 corners of the envelope, are on plane, right? But this tip of the envelope is out of plane. So this is carbon 5. This is 1, 2, 3, 4. Okay. And when the cyclopentane adopted this kind of envelope shape, so now all the CH bonds are not quite eclipsed. So avoided this kind of all eclipse, very unfavored torsional strain angle. Torsional strain, yes. Okay, if we go to 6 membrane, now the funny things happen. Okay, 6 membrane doesn't have any strings. So if you look at the planar structure of 6 membrane, it should have a lot of string because all the CH bond will be eclipsing with each other, right? And it should also have an angle string because the 120 angle of the planar structure is very different from, it's different from the 109 degree optimal angle, okay? So what cyclohexane adopt is called a chair conformation. So this is the real cyclohexane conformation. So, oh, no, not this one. Okay, let's see the 3D first. Okay, so why do we call it chair? So we have 4 atoms, carbon 1, carbon 2, carbon 4, carbon 5 on a plane. So these 4 atoms are on a plane, you can see, right? And one of the additional carbon is above the plane. One of the additional carbon is below the plane. So if you look, so if you remember this structure, so this is an angle, this is an angle, and let me show you some chair, what chairs look like. So I need to go back to. So this is a very ugly, very ugly drawings on the textbook. So you can see this is actually what we call a chair. Okay, you put your feet in the on the triangle with the atom below the plane of this 4 carbon, right? And another carbon, you put your head on it, and this carbon is above the plane of this 4 atom plane, right? So and so what we call this is chair conformation, okay? So why this chair conformation allow the cyclohexane to have no string energy? So there are several aspects. So let's consider Newman projection. So if we look through this direction of C1, C2 bond, and this direction of C5, C4 bond. Okay, and then what we see is that, so in the front is C1, C5, C1, C5 here. This is the bridge, which is C6 here, and this is below the plane, which is C2. Okay, so the C1, C3, this is C3. So the C1, C2, C1, C2, C5, C4, C5, C4. These 4 carbon are on a plane. C6 above the plane, C3 below the plane, right? And if you draw the Newman projection of this, you will find that all the hydrogens are perfectly staggered with each other. No eclipse whatsoever. So all bonds are staggered. So that means no torsional string. And because these carbons are very comfortable with each other, like you can see, it's a perfect sp3 carbons. And so that means that they don't. They also they neither have the angle string, right? So all these effects make the string energy of the cyclohexane 0. Okay, so before we move on to talk in detail about these 6 membranes, we need to first learn to draw chair conformation of cyclohexane. So if this is your first time to encounter these structures, it's kind of takes some time for you to practice. Okay, so first you draw 2 parallel lines. Okay, and this one and this one. So this one and this one. Actually, besides these this pair of parallel lines, you can find a lot of other lines that are parallel to each other. For example, this red one, this red one, this red one, this red one. They are parallel. Okay, this straight one, this one, blue one, blue one, blue one, parallel. Okay, and the black one, black one, black one, black one, and blue. So full of parallel lines. Okay, just and that actually can help you draw it. So you first draw two lines like this, and you draw another pair of lines, which is parallel to each other. Okay, but in this time, just notice that one of the new carbon is above, and the other carbon is below the plane. Okay, and you need to draw this carbon and this carbon forward, just past each other a little bit. Okay, like you draw an imaginary line, you pass this line a little bit, pass this line a little bit. Okay, so things become easier. So after you draw these 6 carbons, the last step is just you connect this one and this one, and this carbon with this carbon. Then you have a perfect 6-member ring chair conformation. Okay, and there are another type of 6-member ring, which is draw like opposite direction with this one, but we will talk about the relationships between these 2 drawings. Okay, so 2 parallel lines. Okay, then 2 parallel lines, and pass each other a little bit, imaginary lines, and pass this line, connect the dot. You have another 6-member ring drawn like this. All right, and after you draw the 6-member ring listed here, what you need to do next is so basically these are just the carbon, right? If there are some substituents on this carbon, you need to draw them. And the thing is that to finish the structure by drawing parallel lines again, all right? So if you want to draw those straight, this is perpendicular. So you need to draw the parallel lines, like 6 of them. So at the end, it usually means hydrogen, or if you have any substituent on it, okay? This 6, and then another pair of parallel line like this and this, and finish it with more lines, which is here and yes, and here and here and here. Okay, I know this is kind of, if it's the first time you try to draw this, it's kind of very frustrating. Okay, so I've prepared something on Moodle for you to, to really learn how to do that. So if you open Moodle, so go to class, and you have some additional resources here. All right, click and you have one tutorial for you to learn how to draw a perfect chair conformation. All right, if you download it, it has step-by-step instructions how to draw this and how not to draw this. All right. So this actually was provided during previous organic chemistry classes by a tutor. Okay, but I have an even simpler version for you to practice. Okay, a simpler version is like when you go to your primary school, right? So you learn how to draw A, B, C, and D. So this is much simpler. So I have a print. You can print this out, and you have all the dots, right? You just need to connect the dots. So that's pretty simple, huh? So first you connect the dots to get familiar with this one. So this is different than this one, two different chair conformation, right? Then I have those gray structures. You can just sketch on them, okay? So without the help of dot, you need to draw these, okay? And then I have the last part of this practice sheet is those gray structures, but with substituents on it, okay? So after you really sketched all of them and practice on that, and take out another white paper and try to draw without any of these help, okay? And then with all these practice, I think it will take you like several times to get familiar how to draw the chair conformation, but you will eventually like be very good at it. And this also helps you to draw chair conformations during the midterm better. Okay, if you draw really ugly chair conformations, it's really a disaster for us to grade, you know. So please practice on this. And I think before we end the class, I'm going to show you what. So after we learn how to draw this chair conformations, and maybe next time, yes, there are too much to talk about this time. So we will learn some some definitions and characterization, characteristic points, properties of these 6 member rings. We have axial and equatorial, just like the Earth, and we will eventually talk about phases of the cyclohexane, and then we will talk about the ring flip. So okay, we will. So you see, this is what we learned to draw, and this is another cyclohexane, right? And they are kind of related to each other with a movement of bonds, and we will talk in details about these things next Tuesday. All right. And meanwhile, after this class, please, if you haven't done so, just sign up for the tutorial, and just the nomenclature drill will be ready next week. And I have office hours this afternoon from 2 to 4. So if you have any questions, you need to talk with me face to face. Just knock on my door and come in. And also, if you do not feel comfortable talk face to face, you can send me an email. We can even set up a Zoom meeting with. I can set up a Zoom meeting with you to talk about anything you want about this course. And I remember I forgot to answer one questions about the practice here. So one of you asked me whether it's okay to. Do you have to draw all the conformations of this one? So do you have to draw all the conformations? So again, I will be very clear in the midterm. Okay. So if I want you to draw all the conformations, I will say please draw 6 conformations, like 3 staggered, 3 eclipsed. If I just say draw the most stringed one, you just give me the most stringed one. You don't have to repeat it with another one which has the same string. Okay. Just give me the most stringed one. Okay. Again, so I will be very clear in the midterm. So